All right, thank you for the introduction. My name is Renaud Danhaive, and as you said, I'm a PhD candidate at MIT working with Professor Caitlin Mueller. And today I will talk about the structural patterning of surfaces, which is a research that introduces new computational workflows. Thank you. That introduces new computational workflows to design structural patterns on surfaces for architecture. Structural patterns can create meaningful difference on an otherwise homogeneous architectural surface. By introducing thickness, ribs, or voids, patterns can accumulate material where it is most useful. And patterns in architecture have long been used for symbolic meaning or ornamental purposes. Often associated with vernacular architecture and symbolism, patterns can be both ornamental and functional. And we can see that there's been a recent surge in the performative use of patterns, particularly in structural engineering, as contemporary structural engineers and architects use them to reduce structural weight and to provide aesthetic and experiential qualities to their designs. In addition to that, structural patterning with greater complexity is enabled by the recent advancements in digital fabrication. Even the academic Robert Ricollet acknowledged that for all the diversity of his research in designing lighter structures, his pursuits could be summed up to making holes. And at a fundamental level, designing a structural pattern on a surface or in a continuous medium, it is about making holes, choosing the location, the shape, the sizes, etc. In fact, a variety of methods have been developed during the last 30 years to help structural designers make holes. An entire research field, topology optimization, was born for that purpose in the 1980s. And topology in structural engineering refers to the way elements connect in a truss, for example, or the way regions of solid or void alternate in a continuum. In other words, designing a structural patterns is designing the topology of a surface. Initially used by engineers in industries with stringent structural performance requirements like aerospace industry, topology optimization is now integrated in add-ons for CAD environments and has slowly found its place in the toolbox of architects and engineers. But topology optimization does not care for art, and it has not been developed for architectural design. Rather, its best methods leave little room for authorship beyond the definition of a design domain, and the obtained results are gradients of density represented by pixels or voxels of material, which are hardly a representation of anything buildable. In addition, no control is possible over the shapes of the apertures, the locations, the numbers. As a result, topology optimization merely is a source of inspiration for structural designers rather than a rich design methodology. Recent work in the computer graphics community is focused on developing methods that map regular patterns on meshes as to produce 3D printed artifacts with desirable elastic properties. But while the work is technically excellent, it was not developed with design in mind, and a lot of the drawbacks of traditional density-based methods remain. In addition, because these methods rely on material density rather than the actual shape of the apertures, they don't account for the true material behavior around the hole where it is prone to high stress concentrations. Another simple heuristic to design pattern structures is to analyze the forces, the stresses in the base structures, and then nucleate apertures or scale pre-populated cells according to the stresses. The higher the stress, the smaller the aperture, and vice versa. The simplicity and ease of application of this rule is appealing, but unfortunately, this naive approach is misleading as holes disrupt the flow of forces in a structure, especially when they're large, rendering the initial stress configuration completely obsolete. But despite the flaws of such methods, the underlying assumption is fundamentally correct. The structural hierarchy that naturally occurs in continuous media can indeed be leveraged to save material, but there is a need for systematic and creative ways of exploring such hierarchy. This research seeks to fill that gap, and specifically it does so by manipulating exact geometric artifacts, like curves and surfaces, rather than relying on density-based approaches. Now, this presents a lot of computational challenges, in particular in terms of speed, and developing the workflows involved a lot of technical, theoretical development, which I'm going to briefly explain right now. To understand the method we developed, we must go back to the basics of CAD. And when we model in a surface modeling software, we almost always are sculpting parameterized surfaces. Parameterized surfaces like this one map a 2D parametric space onto a surface in dimension 3. Any two-dimensional object defined in the parameter space undergoes the same mapping, and that makes for a convenient way to describe map patterns. Of course, manipulating pattern directly on a non-planar surface is hard because it entails manipulating 3D curves while enforcing that they lie locally on the surface. But doing so in the parameter space automatically ensures it. Computationally, this is less intensive, and this is why our methods focus on patterns as they exist in the parameter space, and all the operations that we do happen in the parameter space in 2D. Now, with regular finite element methods, a 3D surface needs to be trimmed and then meshed to become analysis ready, an intensive process that is unsuitable for the exploration of pattern variations, because every time you change the initial pattern, it requires retrimming and remeshing at each step. And of course, meshing is a time-consuming process. Maybe not here, but especially for complex topologies, because it involves a lot of geometrical computations. Same goes for trimming. With our method, all the numerical legwork is actually performed in the parameter space. Therefore, we can fully describe the patterns in the latter, while the 3D trimming curves never need to be accessed nor manipulated by our algorithms. As a result, it allows to quickly exploit pattern variations in a performance-driven way. Our method is based on recent development in structural analysis that you may know of, which is called isogeometric analysis. While traditional FEA relies on using a meshed approximation of a model geometry, IGA, isogeometric analysis, does not require any form of meshing or further meshing because it relies on a mathematical structure already present in the parameterized surface you're modeling, which really allows for a streamlined modeling workflow between parameter and physical space. And that really justifies its use for the present research. IGA is, in fact, very similar to classical finite element analysis. It requires an integration over the domain in order to build the matrices used in analysis. But in IGA, integration is performed over the parameter space. So we could go back to that idea that everything happens in the parameter space in 2D, which is itself divided in quadrilateral cells. An initial drawback of isogeometric analysis was its inability to deal with trimmed geometries, which stems from the absence of a mathematical relationship between parameterized surfaces and their trimming curves. As a result, in the early days of the method, geometries with complex topologies had to be reconstructed with multiple surfaces to become analysis ready, which essentially defeated the initial intent of the method itself. So we're performing integration over the parameter space. But when the parameter space is made up of alternative regions of void and solid, there is a need for an adapted integration scheme. Our method identifies trimmed integration cells and recursively builds new cells corresponding to the trimmed geometry. The parameter space is divided into rectangular cells. Its intersections with the trimming pattern, which can be really dense, as shown here, are found in a ladder split to reconstruct new integration cells. So I'm not going to dive further into the details of the method, which can be found in the paper, but the big takeaway here is that our method and algorithm are able to analyze fast and accurately surfaces with dense trimming patterns, which allows the workflows introduced next to be integrated in exploration or optimization strategies, which was hardly possible before with the classical finite element analysis approach. So this work relies on two geometric workflows integrating operations applied on patterns, including scaling, grid distortion, curve insertion, modification, etc. The first scheme, called fixed top for fixed topology, starts with an input topology and and associated connectivity that remains unchanged throughout. The topology is populated with predefined shapes, and these cells can then be scaled using controlled surfaces. Similarly, the designer has the possibility to incorporate distortion of the initial topology, again using controlled surfaces. The second scheme, EvoTop for evolutive topology, is much more simple. It's a simple cell insertion scheme, and starting from a solid configuration, cells are inserted and improved successively as many times as prescribed by the designer. What lies at the core of the idea here is that both modeling workflows can accommodate an infinite variety of patterns. They are open, flexible, and can be combined or augmented with additional geometric rules. So, as we just saw in the fixed stop workflow, we make use of surfaces to control the pattern variations in the parameter space. Specifically, the vertical distance between a 2D cell in the parameter space and a surface defined over the parameter space informs its scaling. Using such a control surface has two advantages. First, it allows for a smooth gradient across the pattern, but most importantly, it allows to drastically reduce the number of variables controlling the pattern thanks to the surface. In addition to scaling, control surfaces can also be used to distort the initial topology. Using the same strategy, an initial cell topology is distorted through the use of two control surfaces. The X and Y control surfaces move the topology points in the X and Y directions while connectivity is maintained. And the workflows introduced can be used to generate pattern geometries at will, but they become powerful when integrated with strategies of performance-driven exploration, like the ones Caitlin introduced earlier today. Here I've put a general constraint optimization problem, which can be formulated as follows. So essentially, when you're solving an optimization problem, that's what you're trying to solve. F is some objective, so in structural design it could be weight or compliance. X are the design variables, like the control surfaces, the topology of the pattern. And finally, we have the constraints, which can be displacement constraints or material use limits, for example. What's important is that in the workflows, all the design variables can be modified through manual exploration or can be controlled by an optimization algorithm. So we can use optimization algorithms on top of those geometric workflows. So now we've sort of introduced the overall approach, the theoretical development that was needed to make this computationally feasible, as well as the workflows. But let's look at two design examples to understand the potential of these strategies. First, we'll look at a very simple steel prismatic beam, which is optimized for stiffness, by introducing 500 perforations generated by the fixed stop workflow. Compliance, which is measured in terms of strain energy, is minimized, and the problem is constrained by a minimum material savings target of 50%. In other words, we're trying to make this beam as stiff as possible while saving at least 50% of the material. So this video shows the prismatic beam simply supported, mapped with a triangular pattern, and optimized with a global scaling control surface on the right. And the beam deflection is indicated by an overlaid color map with white corresponding to zero displacement. Below, we can see the normalized strain energy shown decreasing as the algorithm progresses. In the first stage, we had a stochastic optimizer which searched the design space chaotically, and then the solution is finally optimized locally with a deterministic algorithm. And it converges to this result. So here we can see the actual final configuration of the beam after the optimization process. Above the starting configuration, below the optimized one. So in optimization, there are two strategies possible. First one consists in removing material from a solid. The second one is consists in adding material where it is needed, starting from a configuration with little solid material. This is the strategy we employ here. That's why you see at the top, the starting configuration has very little material. Here again, we can see the optimization process with the two-pass optimizer, stochastic and deterministic, which distributed material where it is most needed. For stiffness, by scaling the pattern through the control surface, And the result is a tide arch-like distribution of material. Here's an example of the same beam with different boundary conditions. It is now a cantilever, and above we have a result obtained as before with the global scaling surfaces, where you can see the material accumulate over the support as we'd expect, but we've also added more control variables on the pattern with the use of distortion the surfaces, which further decreases the strain energy by reorienting the material on more efficient path. And of course, the second design decreases the normalized strain energy even further. And nowadays, thanks to advancement in digital fabrication, structures like these can really easily be built. And there's a potential to invent structures that delight and save material through structural patterning. So far, we've only seen a 2D example, which is interesting, but the real power of the ideas presented here is best illustrated when applied on curved shells. Indeed, the methods we developed do not require physical surface trimming, and all geometric operations applied on the pattern are two-dimensional. As a result, the optimization process is less computationally intensive, and all the geometric operations remain tractable. So here we have a doubly curved shell, which is optimized for strain energy with a saving target of a minimum of 30%, which we will optimize using both fixed top and evotop. And the shell is supported in all directions along its base edges and loaded by its own self-weight, which results in the displacement map shown there on the right. Similarly to the prismatic beam, we use the fixed top workflow to design a structural pattern on the shell with distortion and scaling. The structural pattern, as before, saves material while increasing the stiffness of the structure by redistributing loads. And of course, with this method, we're free to explore any whimsical pattern we'd like, which is really what lies at the core of the method, is that we're able to integrate the design intent into what was initially an optimization problem. Here we use the evotop workflow. The start conditioning is the solid unpatterned configuration. Successively, holes completely arbitrarily with random shapes are added and subsequently optimized. First, introducing holes greatly increases the compliance of the structure. As the optimizer slightly modifies the shape and location, the stiffness improves. The example shows the usefulness of evotop to handle completely arbitrary designs and integrate any possible design intent. In particular, even with arbitrarily drawn apertures like this that don't really make sense, the system was able to find a solution performing better than the solid one. Now, the previous example, albeit arbitrary, shows the potential of the workflow to design shells with large apertures in a structural mindful fashion. For example, this project, which was designed in a highly seismic area, the position of the holes is incredibly important for the structural behavior of the architectural surface. The tool we developed allows to easily explore the position, size, and shape of these holes while ensuring that the structure is sound. Now, this slide shows you the breadth of patterns that can be explored in a performance-driven way by the workflows introduced. In terms of strain energy, all examples perform better than the initial solid configuration. So, like topology optimization techniques, our method seeks to improve structural performance, but it does not focus on finding the one best solution. It looks for a way to incorporate a designer's intent and empower exploration of ideas through state-of-the-art optimization algorithms. Designing pattern structures required significant expertise and complex computational systems. We developed strategies which are aimed at maximizing structural performance while offering a diversity of solutions which can respond to non-structural priorities. The tools were developed in the Rhino Grasshopper environment, and they will be soon available for download. I would like to conclude by saying that the introduced modeling system capitalizes on the theoretical development we developed, and it provides simple ways to integrate creativity and rigor in the conceptual design of such complex structures through the combination of geometric rules and optimization techniques. Because the method is seamlessly integrated into the CAD environment, it is possible to interweave pattern modeling and structural optimization in design-oriented ways, and it offers designers creative and systematic ways to explore uncharted territories in structural design for architecture. Thank you.